And this is the first curve, but it's not all. The cell is filled with water, and what you additionally get is hydrodynamic interactions. And these hydrodynamic interactions is the second piece, which then brings down the diffusion to also the experimental values. Okay. Monte Carlo methods. So this is an explicit equilibrium method. As I told you, it is about throwing dices. But what are you actually throwing dices on? It is configurations of the system. So actually, if you think what equilibrium statistical physics is about, you have an ensemble of configurations. These ensembles are distributed according to the Boltzmann distribution, and then you take average over this Boltzmann distribution. But how do you get a representative configuration from these ensembles? And this is about Monte Carlo. So this is essentially sampling the Boltzmann distribution. And it works very easy, and so this is a scheme which I briefly described to you. So you start with some configuration, you put particles anywhere in space, and then you propose to displace one particle or many particles, then you calculate an energy change, and then you say, okay, if this energy change is negative, then you accept this move straight away. So you accept this new configuration because the energy has decreased. That is good for Boltzmann. If the energy increases, you accept this only with a lower probability than 1, which is given by the Boltzmann factor itself. And you do this over and over again, and then a theorem guarantees you that you end up in the correct Boltzmann distribution. And with that, then you can collect statistics, and this is the nice thing, you can access states in your system which are sometimes hard to reach by dynamics. Because in Monte Carlo you can play tricks. You can take whole chunks of particles and move them somewhere else in one step. You only have to think that you do the there move and the reverse move with the correct probabilities. But with that you can sample the full phase space quite easily. Okay, and therefore it is good to compare Monte Carlo and molecular dynamics. And here I've listed a list of criteria and actually what these two methods do. In Monte Carlo, we don't have an actual dynamics for an expert view. It is only a trick of generating configurations. So what creates equilibrium averages. In MD, we have explicit time evolution, and averages are sort of a consequence of that. So it has more, if you want. In terms of moves, I explained to you Monte Carlo, you have unphysical moves, and they help you in equilibrating systems, and this is in MD not necessarily the case. Monte Carlo's equilibrium transport properties are difficult. In phase equilibrium, this is really the realm of Monte Carlo because it has special techniques. You can treat all statistical ensembles efficiently, and this is actually where you don't apply molecular dynamics. Yeah. Free energy methods, which are interesting, as I explained to you, for biosystems, for instance, can be done in both things. Large systems I think behave similarly in both systems. And if you think, say, about chemistry, then you would also go back to molecular dynamics, since again there's no time evolution in Monte Carlo methods. Okay, here is a Monte Carlo example, which comes also from, I would say, applied polymer chemistry. And so what has been popular, maybe it's about 15 years ago, was mixing polymers with nanoparticles. So on the one hand, so you have nanoparticles which you put layers on, so you graft nanoparticles on surfaces. And on the other thing, you put everything into a polymer bath. So this is up there what I described here. So you have nanoparticles of polymers and you put this in the polymer matrix. Again, when you simulate these things, you throw out the matrix and you only simulate those and you treat the interaction between those by effective interactions mediated by the homopolymers. And then you ask, what will you get? What type of phases will you get depending on these parameters? So you can think what parameters you have. You have grafting density. How many hairs do you put on the nanoparticle surface? How long are these hairs? How long are the polymers in the matrix or the bath? And then you have interaction parameters and so on. And this is actually an interesting example that you have a system which is quite boring if you take the individual components. Polymers, polymers, polyethylene, whatever, nothing fancy. You have round nanoparticles with a little bit of polymer, spherical power. Very uninteresting. And now if you mix those, and all of a sudden, these isotropic nanoparticles assemble into anisotropic structures. So this is what you want to get. And this depends critically on the number of hairs that you put onto the nanoparticle surfaces. Here are examples that I show. So I go from N to 0, so you only have these nanoparticles in solution, nothing happens. So you have now 2 hairs, 5 hairs, going up to 8 hairs. And what you do is you go from cylinders to hexagonal sheets, then down to strings, and then you disperse the system. The whole system, it takes too long to explain. This is not about the attraction between, say, the hairs. So it is a very delicate competition between entropy of the polymers, entropy of the hairs, and the residual nanoparticle attraction. And then these people who did this, I gave a list of references previously. They compared their simulations, all has been done with Monte Carlo, to the experimental things. And this is usually also what you find in accuracy. So it's the typical soft matter accuracy. You have a reasonable quantitative explanation of these things going on, but being quantitative is super hard. Because, I mean, this experimental system is messy. So you have this polymer bath, is polyviscous, it consists of complicated polymers, and then in the end, the nanoparticles, they are also sort of synthesized, not very well-defined particles where you put something on. The number of hairs on the nanoparticles differs, of course. You cannot control this precisely. And then you try to map it to a very simple simulated system. So it is about understanding, not necessarily full quantitative agreement. So this is more or less a final slide where I also try to say that not only in molecular dynamics, but also in these coarse-grained simulations and Monte Carlo systems, there are packages who do the job. So here I listed a few very popular ones, ROMEX and NAMS for Oettel simulations. ROMEX is for biology, NAMS is for more soft matter chemistry, I would say, material science. And OD is a super fast GPU native system which can do molecular dynamics and also Monte Carlo. EMBER is also for biomolecules. And what I want to say here is, what I want to encourage the students is, you should try this out. So maybe you feel also a bit motivated by the lecture. These days it's actually quite easy. Maybe you have a problem in the lab and then you think a little simulation would help. Take your favorite AI tool and ask it, okay, what type of simulation package would you recommend? Can you help setting up a simulation for me? And it is actually quite rewarding because you get some results quite easily. Most likely these results will not really apply to the system, but you get insights easily. Yeah? So you don't need to write a simulation code, but you only need to write clever prompts in order to do this. And what I want to emphasize, it's not about cheating here, but it's really, it could be about generating insight about your own system. And maybe this is also a part of you. And with that, yeah, this is now the final summary slide. Again, there's the summary of all the different methods. So simulation is not a black box, but it's actually a theoretical tool with an atomic resolution, so sort of microscope. And I encourage you to try this out. Thank you.
Thank you, Professor, for the lecture. Vamos passar agora para as perguntas.
Yeah, thank you very much. Perhaps even inspired by your statement about simulation not being a black box. Where does AlphaFold tools fall within this realm, or do they not fall within this realm? Are they complementary? And can you still get physical insight from tools like that?
I mean, AlphaFold is not linked to explicit simulation results. Actually, AlphaFold, I mean, the base is, so the base for AlphaFold are these folded structures that are recorded in the protein databases. And when the problem has a very long history where people tried, even without AI, to construct the rules from this database. And AlphaFold has brought this to a level, unpredicted level, let us see. So that actually machine learning sees their connections, how different strands of proteins behave in different proteins that was hitherto not really accessible. So it is actually only, the ground truth is a huge table of folded structures. But there are almost no dynamics data in there, if I'm rightly informed. So I would say that here, molecular dynamics can contribute pathways, and from pathways you can learn and also other things that AlphaFold cannot predict.
We have another great question.
Professor, thank you for your presentation. My question is somewhat in the same line that the previous question. For what I did understand, you did not use AI in your research. Maybe it was not updated, but you see AI doing a better job than models such as you presented here. And because from my point of view, AI is very good to this kind of problems of many bodies, some interactions that is not obvious to us but has a mathematical relation to them. So, do you think maybe the use of like a custom machine learning model would like overtake these models, like with Carl simulations and other techniques, or it's too early yet to say something like that?
So currently, my opinion is that the simulation tools are the ground truth for AI. So what you would like to do is, you would like to condense the simulation information into more efficient models. So this is actually my my actual research on density function theory. So what I try to do is I take simulation data and I encode the simulation information into a classical density functional. And from that classical density functional, you can derive many more quantities that would be hard to get them from simulations. So this is currently my approach. The other thing that you could ask is that you, if you have a very costly simulation, that you have a sort of an in-place AI model which simulates the dynamic, the effective dynamics. Yeah, but on the other hand, again, you have to train it by explicit simulation results first. But I would agree, this is probably also one of the future directions. I don't know how general this will be, or whether this will be applied to very specific processes that are then trained and parameterized by the AI dynamics or so. But yeah, this is easily imaginable. Yeah.
A gente tem aqui para mais uma pergunta.
My question is concerning how to include in your atom simulation the entropic force. You show the several terms in the Hamiltonian for an intermolecular force. But for instance, how to include hydrophobic effects, essential for determining the final functional form of a protein. How to include the environment, all the environment in all atom simulations.
Yeah, okay. Okay, but essentially, I would assert, I mean, this is part of the non-bonded ones. But the difficulty is that you have a Lennard-Jones type interaction, Van der Waals type interaction between pairs of different molecules, and there you enter sort of parameterization freedom. Yeah? And then, but with that, with these parameters that depend on atomic species 1 and atomic species 2, essentially you include also all the hydrophobic effects in there. Yeah? So one sees that, and if one tries to simulate phase behavior of systems, you know, if you have a hydrophobic system, and then you can also see the onset of drying around this hydrophobic object, and this is determined essentially by these Lennard-Jones parameters. It works. Yeah? But this was this warning I said. So usually force field people have optimize these parameters and the partial charges to a certain set of experiments or to a certain set of other observables, and you have to read carefully what observables these are. And you're right, if there is nothing of hydrophobic effects in there, then you might have a super failure with your force field. So you need a force field which has somehow taken into account this. And yeah, this is warning, I would say.
Dá tempo ainda de mais uma pergunta rápida, se alguém tiver?
Nossa,
Então vamos encerrar, vamos agradecer.
Nossa, atrapalha.